While the explicit objective of exercise 2128 may seem different from the exercises we've done so far, namely it's to draw the mechanism for an acid-catalyzed hydrolysis of an amide, it's actually the same exact thing. It's just another example of a nucleophilic acyl substitution. And the only difference is what the leaving group is. Here, the leaving group is going to be the nitrogen in the amide. Remember, an amide is where you have a carbon double bonded to oxygen, single bonded to an amine. So single bonded to a nitrogen, but that has single bonds to other things. So here we have a cyclic amide, and this one is particularly relevant because this is actually a beta-lactam ring, which is very common in penicillins and cephalosporins, those antibiotics, those most common of all antibiotics prescribed in the United States. So a cyclic amide, we saw how this is an amide because you have the carbon double bonded to oxygen, single bonded to the amine. An amide that goes in a ring like this is called a lactam. So that's a version of an amide. A cyclic amide is a lactam. The carbon that has the carbonyl on it, that's the carbonyl carbon. The one next to that is called the alpha carbon, and the one after that is called the beta carbon. And so the nitrogen of the amide is attached to the beta carbon of the ring. And so this is called a beta lactam. This opens up a little better than normal amides because of the ring strain. So for example, these two carbons here, those are tetrahedral. They would prefer to have 109.5 degrees between them, but as you can see, the bond angles are forced to be 90 degrees. And so there's a lot of strain there. That's true for the nitrogen too. And then this carbon right here, is sp2 hybridized trigonal planar. It would prefer to have 120 degrees, and it's being forced to have 90 as well. So that ring strain, the strain that comes from forcing this into the shape of a small ring, helps to make this beta-lactam structure a little more reactive than amides otherwise are. Amides are among the least reactive of the carboxylic acid derivatives. And you can see that reflected in biology because amides appear very, very often. Proteins form when amino acids come together and create amides. And we'll see that in the next exercise, the mechanism for how that happens and how you can recognize amino acids. But proteins are long strings of amides. And so those amides have to be stable structures. If they weren't, they wouldn't last very long, and they never would have been selected to create the structures of proteins, because then proteins would just crumble as if they were built of sand. So amides in general are relatively stable, and normally you would see that. I mean, perhaps at first you'd say, well, the carbonyl carbon is bonded to oxygen twice and nitrogen once, so it's losing a lot of electron density. But a similar thing happens here as happens in esters. The nitrogen here has a lone pair that is allylic to the pi bond. And so the lone pair electrons can go to, there's another resonance structure where these go toward the carbonyl carbon, and this bond opens up. But you can see how these electrons are contributing electron density toward that carbonyl carbon, making the slightly positive charge smaller, and so stabilizing it and making it a weaker electrophile, and therefore not as reactive. And so if this is not a very reactive structure, how can we make it more reactive? The way that you influence stability or reactivity is through proton transfer. Proton transfers either add charge onto a molecule and make it more stable, it's more reactive, or take charge off and make it more stable, less reactive. So here, the only thing that we have to work with is hydronium and a little bit of heat. So hydronium has the 3 bonds to hydrogens. Because that oxygen has 3 bonds, it has a full positive charge. And the slightly negative oxygen in the carbonyl attacks one of these slightly positive hydrogens. Those hydrogens are losing electron density to the oxygen, both because of electronegativity and because the positive charge there is sucking electrons away even more powerfully. So that carbonyl oxygen steals one of the hydrogens, and the electrons snap back onto the oxygen to stabilize the positive charge there. So you could see that proton transfer. Now, what we get after that is, actually, what we get after that is, first, the hydrogen moves onto that carbonyl oxygen. Now, the carbonyl oxygen has 3 bonds and therefore a full positive charge. The hydronium lost the hydrogen, the electrons snap back onto the oxygen and stabilize what was a positive charge there, and that turns just into water. So we have this water. Okay, so what difference does that make? How does that proton transfer make the carbonyl carbon more electrophilic and more reactive? Well, before, the carbonyl carbon was losing electron density to the oxygen because of electronegativity. That's still happening. But now it's losing electron density even more because the positive charge is pulling it. And so it loses much more electron density, and the slight positive charge on that carbon is much bigger. And so you can see how it went from being a weak electrophile to a stronger electrophile. An electrophile strong enough that even the slightly negative oxygen on water, which is stable, water doesn't have a full negative charge, so it is perfectly fine not reacting, but because this is such a strong electrophile, it induces this water nucleophile to attack, the pi bond breaks, and the electrons go onto the oxygen to stabilize the positive charge there. So this is one of our essential steps in any nucleophilic acyl substitution, nucleophilic attack. Okay, well, after that step, we will now have our famous tetrahedral intermediate. This, what was the carbonyl oxygen, only has 1 bond to that carbon, still has this hydrogen, and there's a bond to the water. Now the oxygen of the water that added has 3 bonds, and therefore will have a full positive charge. The nitrogen also has its hydrogen still. So this is our tetrahedral intermediate. Now, you may look at this and see this water and think, that's a good leaving group, and it is. And it could come off, which is why this previous reaction was reversible. But after it comes off, it can attach again, and so you have both of these forward and reverse reactions happening at the same time. In the meantime, some of this does not come apart. Some of this undergoes a different reaction. This nucleophile that came in can be stabilized. Right now it's too reactive. It's a good leaving group. We want to make it less reactive. We want it to stay on the molecule. So how do you change the reactivity of things? You do a proton transfer. Here, there's a positive charge here. If we remove an H+, that will become neutral and it will become stable. So we can take this, we can take a water molecule from the solution and the slightly negative oxygen can steal one of those slightly positive hydrogens. The electrons can snap back onto the oxygen to stabilize the positive charge there. So after that proton transfer, to stabilize that incoming nucleophile, we will have hydronium. That hydrogen will move over to what was water. Because that oxygen has 3 bonds, it now has a full positive charge. The electrons that were here are going to go back onto that oxygen and so stabilize what was a positive charge there. And so we're left with this more stable tetrahedral intermediate. Well, if you think in terms of the grand sweep of this reaction, where we take our leaving group and we replace it with our nucleophile, we've done the first half. We've added the OH on. The nucleophile is there. All we have to do is remove the leaving group. So the OH, you can see, is there. We've added that on. It's there, stable now, and we just have to remove our leaving group. But right now, this is a bad leaving group. If this were to leave as it is, take those electrons, you would end up with a nitrogen that would have a full negative charge. It would have two lone pairs. It would have a hydrogen, would have the carbon, and it would have a full negative charge. And that's very unstable, because nitrogen is not a very big atom, so it's not able to dilute or spread that negative charge out. In other words, because if it left, it would be unstable, it is a bad leaving group. And so we have to make it a better leaving group. Now, a bad leaving group, that means it's not reactive enough. If we want it to react and leave, we have to make it more reactive. How do you change the reactivity of things? You do a proton transfer. So this has no charge. We want to give it a charge so that it will be more reactive and leave. The slightly negative nitrogen attacks one of the slightly positive hydrogens on hydronium. The electrons snap back onto the oxygen there to stabilize the positive charge. And so we move a hydrogen from one atom to another, or from one molecule to another. So that's our proton transfer. So the hydrogen moves over. This lone pair is used now in a bond to a hydrogen. The nitrogen has 4 bonds. And that gives the nitrogen a full positive charge. And the water has no charge because one of the bonds became a lone pair. Okay. So now we have a good leaving group. Our leaving group is a good leaving group. So all it needs is a slight push and it will come off. The push comes from the lone pairs on one of the oxygens. And it doesn't matter which one. Both of these OHs are both OHs. So these oxygens are slightly negative, and the carbon that they're bonded to is slightly positive. It's, after all, bonded to 1, 2, 3 electronegative elements. All of those are stealing, funneling electron density away from it. So it's slightly positive. The oxygens feel the slight positive charge. The lone pairs want to form a pi bond to it, so they move in that direction. But in order to make room, something has to leave, and it kicks the good leaving group off. So what we have here is the other essential step in any nucleophilic acyl substitution: loss of a leaving group. And when that leaving group leaves, we end up with a double bond here. So we still have the hydrogen, still have the oxygen. We have a double bond to this carbon in the ring. The other OH is still there. Notice how many carbons we have. So we have 1, 2, 3, and then the nitrogen. So here this is going to be 1, 2, 3, and then the nitrogen. And the nitrogen has 2 hydrogens on it. And so 3 bonds. So it is now stable and doesn't have a charge. Okay, the one charge that is on this molecule is on this oxygen here, because that oxygen has 3 bonds. So it's unstable. And so this is really making this carbonyl carbon here a really strong electrophile. This can attack it again, and that would bring us back to our ring. That's why this is an equilibrium reaction. So it could come undone, but then it can, the ring could form again, but then it can come undone again. And so these 2 molecules exist in an equilibrium. And while this exists, another thing can happen besides the ring reforming, because the nitrogen attacks as a nucleophile. And that is that you can stabilize this carbonyl oxygen. We can take the water that we had in the previous example, and that can do a proton transfer. The slightly negative oxygen can steal the slightly positive hydrogen. The electrons can go to stabilize that oxygen. In other words, we've taken something that was too reactive, and we've made it more stable, we've affected the stability or the reactivity of a molecule by doing a proton transfer. So what we have as our final molecule is the double bond to the oxygen with an OH. So this is the OH. 1, 2, 3 other carbons with a nitrogen attached at the end. Oh, excuse me. I actually drew too many carbons here, forgive me. This carbon number 1 is the carbon that becomes the carbonyl carbon. This carbon here. So this is actually carbon number 1, 2, and 3. So now I've become a cautionary tale. So make sure to carefully count the number of carbons and number them diligently, because it's so easy to have the wrong number of them. So there we have that. I apologize for that mistake. So now we have that carbon chain, we have the nitrogen on the end of it, and we've done our nucleophilic acyl substitution. We also have hydronium crashing its way through the galactic mosh pit of the solution. And that is our answer. We have taken an amide and broken it off into a carboxylic acid and an amine. And the ring has come undone. So we've taken our amide and broken it off into this reaction here. Now, the product here suggests one other thing that's going to happen, and it makes a really good point. It reminds you of one feature of amines that may not come immediately to mind. Notice the amine that they have here has 3 hydrogens on it and a positive charge. The one that we drew at the end here only had 2. And so what ends up happening is you know that the carboxylic acid hydrogen is acidic. And you also have acid in the solution. But to get this molecule, because the solution is acidic, it takes the hydrogen off of the acid, the nitrogen. The nitrogen is a base. You'd remember from even general chemistry when Bronsted-Lowry bases were introduced, ammonia, NH3, is the poster child of a Bronsted-Lowry base. It has that lone pair there that can accept H pluses. And amines are just derivatives of ammonia. Ammonia, you can imagine ammonia as sort of the nitrogen version of water. Nitrogen with just hydrogens bonded to it. And amines are like the nitrogen version of alcohols. They're derivatives of ammonia, just like alcohols are derivatives of water, where you replace one of the hydrogens with a carbon. So because, just for the same reason that ammonia is basic, amines are basic. They have that lone pair that can accept hydrogens. And so if you're doing this in an acidic solution, this slightly negative nitrogen can act as a base, steal one of the hydrogens from the hydronium, have the electrons snap back on there, and we'd be left with the same molecule, but with a positive charge on the nitrogen here. So that will be bonded to 3 hydrogens, and this will have a full positive charge. So that's just that one extra proton transfer at the end of this mechanism to illustrate the fact that amines are basic. And that will become really important when we get into the amine chapter in the future. It also is important for the behavior of amino acids, which have amines on them. All right, so there is our process. We've turned an amide, carbon double bonded oxygen, single bonded to an amine, into a carboxylic acid and an amine. We've replaced this leaving group with our nucleophile. The overall process is similar to the overall process we've seen before of nucleophilic acyl substitutions. Every time we've seen a nucleophilic attack and loss of a leaving group. Oftentimes, especially in the case of esters and amides, because they're not as reactive, we have to do a lot of proton transfers to influence the reactivity of the molecule. And that's especially true when you're doing an acid-catalyzed reaction. And then at the end of this one, there was just one extra proton transfer to illustrate the fact that amines are bases. So we used water to break apart an amide. So this is the hydrolysis of an amide, and we got the reaction going with an acid catalyst, an H3O+. So that's drawing the mechanism for the acid-catalyzed hydrolysis of an amide. Now, just to compare that with this next one is not acid-catalyzed. This is base-catalyzed. So the mechanism that you'd have to draw on the test would be an acid-catalyzed hydrolysis. For the base-catalyzed hydrolysis, though, it's much shorter because even though the carbonyl carbon here is not especially electrophilic, we have an awesome nucleophile. We have a very strong nucleophile. Sodium hydroxide. Sodium is a metal. It gives its electrons away, and the oxygen that it's bonded to gains them and has a full negative charge. So that full charge makes it really nucleophilic. So we can take this beta-lactam ring and we could have the hydroxide attack immediately the carbonyl carbon. The pi bond breaks and goes open. We start straight out of the gate with our nucleophilic attack in this case. And so what we end up after that step is our tetrahedral intermediate. The oxygen there of the carbonyl has a negative charge, which is unstable. So it's flapping around in the wind. It feels the slightly positive charge on this carbon here, and so the electrons in the lone pairs want to slap back down and smack onto that to create a pi bond, but you need a leaving group. Now, we don't have a good leaving group, but we have a really unstable atom. Compare that with this same step in the acid-catalyzed version. When this came down, it was relatively stable, so we had to make the leaving group really good. It had that hydrogen there and no full charge. But here, in the base-catalyzed version, the oxygen has a full negative charge. So even if the leaving group is bad, that nitrogen is only going to be as unstable as this oxygen would be, if not less. And so it kicks the bad leaving group off just because this is so strongly unstable with its strong negative, full negative charge. And so this is the other staple of a nucleophilic acyl substitution. It's loss of a leaving group. So what we form after that is the carbonyl that has the OH on it now. That's this OH here. And we have 3 carbons, so 1, 2, 3, and then the nitrogen with the hydrogen. This has a full negative charge on it, which is very unstable. And it would end up stealing another hydrogen from the acid in the solution, the only acid. And this is one place where another, again, it's interesting to compare between the base-catalyzed and the acid-catalyzed reaction. So here, the only acid we have in the solution is the carboxylic acid. It's acidic because if the H+ leaves, the electrons in the bond can go onto that oxygen and be stabilized through resonance because it's allylic to the carbonyl double bond. Now in the previous case, in the acid-catalyzed reaction, the amine did not steal the acid on the carboxylic acid, it stole the acid in the hydronium because the solution is acidic. So even if it stole this other hydrogen, the solution would just slap another one onto it. So the product you'd have would have the hydrogen on the carboxylic acid because there's so much acid in the solution. It sticks H's everywhere that it can possibly go on the molecule. And that includes the negative oxygen that would be left behind if you removed the hydrogen there. So in the base-catalyzed reaction, there is no acid in this solution. And so there's there are no solvent molecules that this can steal a hydrogen from in the solvent. But there is an acid in this molecule itself, in the carboxylic acid. This can attack that hydrogen. Those electrons can snap back onto the oxygen. And what we'd have at that step is this. The oxygen would have a full negative charge. The nitrogen would have no charge. And you may say, well, isn't this negative charge just as unstable as this one? And it's not, because these lone pairs are allylic to this pi bond, and so the negative charge is really spread out over all three of those atoms. By spreading the negative charge out, you dilute it, and so you make it more stable as you spread it out through space. And so that is our final product, and that's the product that you see happening here. Now, this is not the one that would be on your test, but I wanted to show you this because I think when you see the base catalyzed version, you sort of can appreciate, by comparison, what happens in the acid catalyzed version. You can see that because we had a weak nucleophile, water, we had to do an acid proton transfer to turn this into a better electrophile. And then that led to a whole bunch of other proton transfers, stabilizing the nucleophile once it was on because it was weak. Turning the electrophile into a better leaving, or turning the leaving group into a better leaving group because we don't have anything with a full negative charge here when it slaps down, and having to do a proton transfer at the end. So you can recognize some similarities and differences, hopefully get a better understanding of the acid-catalyzed hydrolysis of an amide by comparing the acid catalyzed version with the base catalyzed one, which you can see has many fewer proton transfers. There's just that proton transfer at the end because amines are basic. They accept H+.